In this video, we're going to use the preset table command to control these 8 LEDs on this rotating strip. This is a great way to help visualize exactly how the PST command works because you can actually see when the outputs change state. This works the same way on any Productivity Series controller. We happen to be using the Productivity 2000 with an HSO module and 2 HSI modules installed. An encoder is wired in parallel to channel 1 on both HSI modules, and we're driving the LEDs on this strip with the HSI outputs through a slip ring so the LEDs can rotate. The HSO module is driving a stepper, and this I/O is being used to enable the drive. Here's the actual hardware we're using. This is the 1024 count encoder on one end of the motor and a slip ring on the other to transfer the signals to the rotating LEDs. We're using ZipLink cables, ZipLink breakout modules, and this stepper power supply. Here's a summary of all the parts we used. Click on the link to go right to the catalog page for that part. Well, let's do a quick example. The HSO is configured to output pulses with no scaling and provide status in these tags. There's a whole video on configuring the HSO, so check that out if you need more on this. HSI number 1 is also set up for pulses, no custom units. The channel status is stored in these tags, and we're using a 4x factor on the input, which means instead of getting 1024 counts out of that encoder, we'll be getting 4096. And here's a key point. We configured the HSI module to reset the encoder to 0 every time the encoder's Z-pulse goes active, which is why we wired him in earlier. And HSI number 2 is set up exactly like HSI number 1. Well, given that setup, all we have to do is enable the drive, tell the motor to start spinning, and then use the PST instruction to control the LEDs. Let's do it. Let's create a contact to turn on the motor enable, and then use a write high-speed output instruction on the HSO to turn on that motor enable output. Because this is edge triggered, we have to create a second instruction to turn the output off on the falling edge of this contact. And we do that by writing a 0 to the output. And let's change this to a rising edge contact just to be consistent. We'll use the vMove instruction to spin up the motor to a given velocity. We want this channel on the HSO to control the stepper motor. We'll create a structure so we can play with all these values in a data view, and we'll use the positive direction only. We don't need jerk, and we'll do an immediate stop instead of decelerating to a stop. There's a whole video on using the vMove instruction, so check that out if you need help here. And let's create a contact to enable the vMove instruction. Let's create an LED enable contact, and then bring up the PST instruction to control the LEDs. We want this high-speed input channel on the first high-speed input module. And we'll use a structure so we don't have to type in all these values. You can create up to 16 steps, so let's use all of them. Let's do something every 100 encoder counts. Don't forget, we configured this to generate 4 pulses for each encoder count, so we have 4,096 encoder pulses around the circle. So at step 16, where we're at 1,600 counts, we'll be just under halfway around the circle. We want to enable the LEDs during the entire step. We could invert that, reset the table, reset the position counter, or reset both the table and the position counter. Let's toggle output 1 every step, output 2 every 2 steps, output 3 every 4 steps, and output 4 every 8 steps. And on the last step, we want to reset the table so this repeats indefinitely. Hit OK, accept the new tags. So we can enable or disable the motor drive, start the motor spinning, and we can drive the LEDs as a function of encoder count. Let's try it. Transfer to the processor, and when done, make sure we're in run mode, and bring up a data view. Let's add our control bits and velocity parameters. Our motor drive is set to 1,000 pulses per revolution. So let's set the velocity to 10,000 pulses per second so we get 10 revolutions per second. And we'll give it a modest ramp rate of 5,000, so it'll take 2 seconds to get there. Enable the motor drive, start the motor spinning, and enable the LEDs. And sure enough, you can see the pattern of the 4 LEDs we were driving from the first HSI module. LED 1 is toggling every step, which was every 100 encoder steps. LED 2, every other step, etc. This is so cool because you can visually see what 100 encoder counts is. And you can see that of the 496 encoder counts in 1 revolution, the pattern is stopping at around 1600. exactly what we expect. And the pattern always starts in the same place because we're using that Z pulse to reset the encoder count, which is right here. Could we drive the 4 LEDs on HSI number 2? Sure. It's wired identically, so let's copy the instruction, change it over to channel 1 of the HSI module in slot 4, which is where the other 4 LEDs are wired, and change the structure name. We just add that to the same enable, and we're ready to go. Transfer to the processor. Make sure we're in run mode and that our data values are still intact. Enable the drive, fire up the motor, and enable the LEDs. Now we see all 8 LEDs generating the pattern. Perfect. Let's take a look at the pulse option. Instead of turning the second HSI module's output number 4 on here and off here, let's pulse it on, get rid of the off, and create a tag to specify the pulse duration. This little blue double arrow reminds us that we can change that pulse duration while the instruction is running. We'll do that in a demo, but it's important to understand that that pulse duration will only be updated each time the instruction is enabled or on each table reset, which for us is right here. So it'll complete the current cycle and then change the pulse duration. It won't change mid-cycle. Well, let's try it. We do want to create that new tag, and we'll transfer the program to the processor. Make sure the processor is in run mode, and let's add the pulse duration to the data view. We'll be rotating at 10 revolutions per second, or 100 milliseconds per revolution, so let's make the pulse duration 25 milliseconds. So now, output 4 should turn on at the start, and it should stay on for a quarter of the rotation. Fire up the drive, enable the motor, and enable the LEDs. And sure enough, output 4 is 25 milliseconds, which is 25% of the 100 millisecond rotation time. Now we said you can change the pulse duration while the instruction is running, right? Well, let's try it. How about 50 milliseconds? Maybe 90 milliseconds? How about 99 milliseconds? Sure enough, only 1 millisecond of the 100 millisecond rotation time isn't lit. Cool. Now it's important to understand the outputs have a maximum off to on time of 25 microseconds and an on to off time of another 25 microseconds. So the worst case output rate is every 50 microseconds, or 20,000 hertz. So if your input frequency is 100,000 hertz, but the output can only toggle at 20,000 hertz, then the smallest input step size in our table that the output can respond to is 5, right? So don't make this step size smaller than what the output can handle, otherwise you won't get the results you expect, especially since this module can handle up to a 1 megahertz input on each channel. Now, can you reset the HSI count while the PST command is running? Sure. You can use this tag in the HSI configuration to reset the count to this value. Just set this tag to a 1 in the code, and the current count will be changed to this. And while we didn't do it in this video, you should always check to make sure that the high-speed module is ready before sending it commands. Remember, it runs independently of the main CPU, so this is the only way you know if it's ready to receive those commands. Just go to the Hardware Configuration, HSI Module, and set up the Module Ready tag here. So if you need to monitor signals from devices like encoders at rates of up to 1 megahertz and use that input to control outputs at rates of up to 20,000 hertz, and you need to do it with precision and accuracy that's completely independent of the scan time or current processor load, then this high-speed input module from Automation Direct is the way to go. And while we associate this with high-speed inputs, don't forget that it works great for low-speed applications that still need that precision and accuracy which is independent of processor load. If you need any help with the Productivity Series controllers, please contact Automation Direct's free award-winning support team. They'll be happy to help. And don't forget the forums. There are lots of experienced automation professionals there that love to share their years of experience. Just don't post any questions directed at Automation Direct support team there. They don't monitor the forums on a regular basis.